Hello everyone. In this video we're going to continue on with lesson 2 by talking more about the standard deviation, which is what we left off on the last time. So the standard deviation is new to us and it has like weird units associated with it. And what that means, and what I mean by that, is when I talk about the mean or the median, if I talk about the mean house price in all houses in Shippensburg, and I say the mean is 42,500, which is not right for house prices in Shippensburg, maybe 150,000, you know that the units on that are dollars. And so 150,000 has immediate meaning to you. But standard deviation, it may still have units, so I could have a standard deviation of $4,000. But what does that really mean? What does that really mean? And so we're going to attempt to describe that a little bit here. In certain cases, the standard deviation can be described in a meaningful way, or easily right now. It can always be described in a meaningful way, but it takes a lot of thought. So here is a nice case. If the data that we're looking at looks bell-shaped, okay, and you may say, well, where the heck did that come from? It seems like it's out of nowhere. And that is sort of true, but it turns out that things that are bell-shaped, okay, or look like a bell, data that looks like a bell, when plotted in a histogram like this on the screen, are very, very common in statistics. And we're going to call curves or data that looks like a bell, we're going to call them normal data. Okay, we'll talk later about this. But now just think bell-shaped. If my data are bell-shaped, okay, looks like this, then we can interpret S more directly. And what I mean by that is it's going to tell us something about how the data are spread out. Okay, more than if it's small, they're higher. If it's small, it's less spread out. And if it's large, then it's more spread out. Okay, so that is the definition sort of that we're going with right now, or that we can understand all the time. In this case, in this special case, when the data are bell-shaped, we can say something more. And what we can say is described in something called the empirical rule. Okay, the empirical rule. And what the empirical rule says is that when I have my mean here, if you can follow my cursor, the center of the data right here is the mean, as we talked about last time, x bar, okay? And when I add the standard deviation, x bar plus s, and when I subtract the standard deviation from the mean, okay, these 2 points, if I do that, then in between them, I know that about 68% of the observations will fall into that. Okay, so when I add and subtract one standard deviation from the mean, then I know that those 2 points, those 2 endpoints here and here, in between those 2 endpoints, that 68% of the observations are going to be in there. Okay, I know that was long-winded, and I'm sorry about that, but between plus and minus 1 standard deviations, 68% of the observations will lie. Okay? When I spread that out to 2 standard deviations, plus and minus 2 standard deviations, then I get that about 95% of the observations will lie between those 2 points. Okay? And then when I take it out to 3 standard deviations, plus or minus 3, then it says that nearly all or all of them are going to be contained. Okay, so this says when data are bell-shaped, that if I add and subtract 3 standard deviations from the mean, then nearly all of the points are going to be between those two endpoints. What does that mean for us practically? Well, if I said that the distribution of IQ scores out there, so everyone has an IQ theoretically, although everyone have not been tested, okay? Everyone has an IQ, and they say that the mean IQ is 100 and the standard deviation of IQs is 16. Excuse me. So the mean IQ is 100 and the standard deviation of IQs is 16. Okay. Also, they say that IQ scores are bell-shaped, okay, and how they turn out. Then I can say that about 68% of all people have an IQ score of between 84 and 116. How did I get those two numbers? I added and subtracted 16 from 100. I could keep on going and say that 95% of all people have an IQ score between 68 and 132. I believe I did my math right there. I'm doing it in my head right now. So 68 and 132. So that means nearly all 95% of all people have an IQ score between 68 and 132. So that tells us something about typical or atypical values. So for instance, if I told you that I had an IQ score of 150, which is extremely high, okay? But maybe you didn't know that much about IQ scores. If I told you then that 95% of all people have an IQ score between 68 and 132, then that tells you something about how high my IQ score is. Okay, so for instance, if it was 150, you should say, wow, I know that almost everyone has an IQ score, rather 95% of people have an IQ score between 68 and 132. So this person is really smart. Okay, of course you could go the other way, and if I have an IQ score of 50, okay, then you could say, wow, this person is not so smart. Okay, so when data is bell-shaped, then I can use the standard deviation to tell me with or in conjunction with this empirical rule to tell me how typical or atypical a value is. And so we'll have a little practice with this. Okay, so another way that we can gauge how surprising or extreme an observation is, okay, so just what I was talking about in the last slide, is with a z-score. Again, this is a term that seemingly comes out of nowhere on you, and that is true. Okay, nothing before this has told us anything about a z-score, but a z-score is going to be extremely important in the rest of this class. Okay, it'll go away for a week or so, and then it'll come back with a vengeance for the rest of the class. Okay, a z-score takes an observation from the data set and subtracts it by the mean of the data, and then divides it by the result. Divides that result by the standard deviation. I.e., it looks like this. Okay, so we have z is equal to x, which is the data point, okay, minus the mean divided by the standard deviation. Okay, you may wonder, why would we do this? This specific operation, i.e. x minus x bar divided by s, is important because the result, z-score, tells us, or the interpretation of that z-score, is that an observation x is z standard deviations away from the mean. Okay? So if we go back to my example before with IQs, that IQs are bell-shaped, mean of 100, standard deviation of 16. If I said if x was 132, so I do 132 minus 100 divided by 16 the z-score would be 2, which says that 132 lies 2 standard deviations away from the mean. Great. What does that tell us? Well, it tells us that it's fairly high compared to everything else. Okay? And especially if the data is bell-shaped, it can tell us how likely or unlikely things, how likely or unlikely or surprising that this observation is. Okay, generally there's a rule that if an observation is more than 3 z-scores, if they have a z-score of more than 3, which means that they're more than 3 standard deviations away from the mean, they are an outlier. Okay, so that word that we talked about before has come up again, an outlier. So if they're more than 3 standard deviations away from the mean, they are an outlier. Okay, so here is a reading assignment, a number of them for you. I want you to look at variability, the empirical rule, and z-scores. Okay, so they'll talk about them in more detail, and they'll actually go through some steps of using them, which is what I'm going to ask you to do. And so I'll follow this by another your turn. Okay, and this is the exact example that I've been using. Okay, suppose that the distribution of all IQ scores, meaning the data of all IQ scores, if I took every single person, found their IQ score, had all of them together, I'm going to call that a distribution, okay, has a mean of 100 and a standard deviation of 16. Using that information, answer the following questions. So I'm going to ask you to find probabilities. And now I may not have used that word before, okay, but a probability is really just a proportion or a percent that we were talking about before. Okay, so for instance, I'll answer number 1 for you. Find the probability that a randomly selected person has an IQ between 84 and 116. Okay, those two numbers turn out to be plus and minus 1 standard deviations away from the mean, and it turns out that IQ scores have a bell-shaped distribution. So I can use the empirical rule to say that the probability that the randomly selected person has an IQ between 84 and 16 is 68%. Okay? And I found that by going back to here, the empirical rule. So again, here's a your turn. Okay? 1 and 2 are about the empirical rule. 3 and 4 are about z-scores.